Imagine you're a graduate student at Princeton, and then your professor calls revealing an idea so incredibly crazy, something no one had ever thought of before. He declared, Feynman, I've discovered why every electron possesses the exact same charge and mass. Of course, I couldn't help but exclaim, why is that? And his answer stunned me. Because they are all just one single electron, constantly oscillating back and forth through time, appearing simultaneously everywhere. At that moment, I thought my professor had surely lost his mind. However, 25 years later, that seemingly insane phone call became the key that led me to the prestigious Nobel Prize. That was the perplexing puzzle my professor Wheeler was diligently trying to solve. Every electron in this entire universe is absolutely identical, not just similar, not almost, but completely uniform. They possess the same mass, the same charge, the same spin, precise down to the very last decimal place. Just look around you. In nature, nothing else operates by such a strange rule. No two snowflakes are identical, no two grains of sand match, and no two stars are exactly alike. Yet with electrons, there are an estimated 10 to the power of 80 particles in the observable universe. A colossal number, a 1 followed by 80 zeros, and every single one of those particles is completely identical to all the others. No one could offer a satisfactory explanation. We simply accepted it as a self-evident truth. Electrons are identical, period. But Professor Wheeler didn't accept that. He yearned to understand. Why is that? To understand more, first we need to know what kind of person John Wheeler was. When I arrived at Princeton in the fall of 1939, I was full of hope to collaborate with Eugene Wigner. Wigner was a renowned figure who would later be honored with a Nobel Prize. However, when I got there, I was informed that I had been assigned to work with someone else, a young professor named John Archibald Wheeler. I had never heard of him, and what was even more surprising was that Wheeler was only 28 at the time. He was only 7 years older than me. In an academic setting, such a small age difference is almost negligible. Most of the professors I knew were older gentlemen, formal in their three-piece suits. Wheeler, however, looked so young that I could have mistaken him for my older brother. What could such a young man possibly teach me? Yet the answer turned out to be everything. Wheeler had once had the opportunity to collaborate with the great Niels Bohr himself. Together, they co-authored a groundbreaking work on nuclear fission. That work was published in the journal Physical Review precisely on September 1st, 1930. Coincidentally, that was also the day Nazi Germany launched its invasion of Poland. However, that was still not what truly made Wheeler special. What truly made Wheeler stand out was his unique way of thinking. His appearance was entirely unassuming, soft-spoken, neatly dressed. He could easily have been mistaken for a bank clerk, but hidden beneath that calm exterior was one of the most vivid imaginations I had ever witnessed. Wheeler often made statements that made his fellow physicists uncomfortable. These ideas sounded more like science fiction than pure science. Later, he himself coined iconic terms like wormhole and black hole. Meanwhile, other professors chose a safer path, focusing only on solving minor problems. Wheeler, however, was completely different. He didn't hesitate to ask challenging, even dangerous questions. Are there questions that make you hold back, fearing you might be seen as inadequate? And what was astonishing was that from the very first moment, he treated me as an equal, not as a fledgling student, but as a genuine colleague. He would often say, Feynman, what are your thoughts on this? Then one day the telephone rang unexpectedly. It was Wheeler. He revealed to Feynman that he had discovered why all electrons possess exactly the same charge and mass. Feynman, with his inherent curiosity, immediately asked, what's the explanation? Wheeler responded with a startling answer, because in essence they are all just one single electron. Immediately after that, Wheeler began to elaborate on his audacious proposition. Wheeler put forth an astonishing hypothesis that world lines, which we typically envision in space and time, instead of merely progressing forward through the timeline, are actually a giant, intricate knot. I struggled to clearly visualize the concept he was presenting. He explained that when you slice through that knot with a plane representing a specific moment in time, you would see countless world lines, and each of those lines would represent a distinct electron. In physics, we often illustrate particles as trajectories moving through space and time. A world line, an electron originating from one point, then moving to another, exists continuously throughout time, like an uninterrupted straight line in cosmic space. Wheeler was proposing a concept truly beyond imagination. Well, what if there were only one single electron in this entire vast universe, just one solitary particle? But that single electron doesn't simply move in a straight line through time. It constantly bounces back and forth, moving forward and then backward into the past, weaving the tapestry of cosmic history like a single thread through a giant loom. At any given moment when you slice through time, that single electron would appear in billions of different locations. It would seem like countless electrons, but in reality, they are all just one single electron, merely at different points on its own journey through time. That is precisely why they are all exactly identical. They are not merely similar, but are truly the very same single particle. And then Wheeler, with a twinkle in his eye, revealed a groundbreaking idea. Imagine if an electron followed its usual trajectory, but then suddenly reversed the flow of time, returning from the future. Its proper time sign would be flipped. And this, astonishingly, is precisely the change in the sign of its electric charge. I immediately realized he meant that when that electron traveled backward in time, it would appear as a positron with astonishing precision. The positron, the electron's antimatter twin, possesses the exact same mass but carries the complete opposite electric charge. Carl Anderson officially discovered it in 1932. Wheeler boldly declared positrons are not distinct particles. They are merely electrons traveling backward in time. An idea that was at once breathtakingly beautiful, astonishingly elegant, and incredibly wild. But then a perplexing question suddenly sparked in my mind. I then asked, Professor, but aren't there far fewer positrons than electrons? If his hypothesis were correct, then every time an electron moved forward in time, it would appear as an electron. Conversely, every time it moved backward into the past, it would take on the form of a positron. Logic would demand equal numbers, but reality is entirely different. Electrons significantly outnumber positrons. Positrons are incredibly rare particles. Most of the universe we know is composed of matter, not antimatter. Yet the one-electron universe Wheeler envisioned would require a perfect balance between matter and antimatter. Wheeler, after a moment's thought, replied, perhaps they are hiding somewhere, perhaps within protons, for instance. And that was his answer to me, that those missing positrons might be concealed in some hidden corner. I always admired Wheeler, but honestly, that answer wasn't convincing enough for me. On that fateful day, a discovery completely changed how I viewed the universe. The idea that all electrons are identical, I never truly accepted that easily. The calculations were consistently off. They just wouldn't align. We had an abundance of electrons, but a severe shortage of positrons. As elegant as it was, Wheeler's theory seemed to have gone astray. Yet hidden deep within that seemingly outlandish idea lay an undeniable truth. A fateful discovery, one that would forever reshape the entirety of physics. Imagine this. A positron, in essence, is merely an electron traveling backward in time from the future to the past. I didn't cling to the far-fetched notion of a universe with only one electron. Instead, I grasped the core idea. Antimatter is simply matter moving backward in time. That was the key I needed. Let me pull back the curtain and reveal why this discovery held such profound significance. Before Wheeler's fateful phone call, we had always assumed electrons and positrons were two entirely distinct particle entities. At that time, we grappled with two separate sets of equations, one for electrons and another for positrons. As a result, the mathematical operations became incredibly complex and unbelievably convoluted. However, if a positron was simply an electron gliding backward through time, suddenly everything became incredibly simple. Instead of dealing with two separate particles, we only needed a single particle to fulfill both roles. From two troublesome sets of equations, we now only needed one. The mathematical operations all at once became astonishingly elegant and refined. I began to contemplate particles through an entirely new lens, no longer as individual entities moving unidirectionally through time, but as flexible trajectories that could bend, reverse, and constantly move back and forth. Direction was no longer the crucial factor because ultimately everything converged into a single physical essence. And this was the initial seed that blossomed into the legendary Feynman diagrams, the simple strokes I used to construct my way of thinking. Imagine these wondrous lines. They represent particles moving forward, backward in time, twisting and interacting ceaselessly. And then many years later, the whole world would know them by their legendary name, Feynman diagrams. However, the groundbreaking idea that antimatter is simply matter traveling backward in time came from Wheeler, from an impromptu phone call with a professor who never hesitated to utter the most seemingly outlandish things. 8 years later, I faced my greatest challenge, presenting all these ideas to the greatest minds on the planet in physics. The time was late March 1948. At the prestigious Pocono Conference, 28 leading physicists gathered at a secluded hotel in the Pennsylvania mountains. It was truly a room full of the most formidable minds one could imagine. Niels Bohr, the great father of quantum mechanics, who once intellectually sparred with Einstein himself, was also present. Paul Dirac, whose prophetic equation predicted the existence of antimatter and who clinched the prestigious Nobel Prize at just 31, was also there. Robert Oppenheimer, the chief architect of Los Alamos and the creator of the atomic bomb, was also in attendance. Eugene Wigner, Enrico Fermi, Edward Teller, Hans Bethe, it seemed all the greatest minds had converged. Julian Schwinger was the first to present. He lectured non-stop all day long, from dawn till dusk, pausing only briefly for lunch. Although his mathematics were incredibly dense, complex, and traditional, astonishingly, the audience kept up completely. They grasped everything. Then it was my turn. I stepped up to the blackboard, beginning to sketch my unique diagrams, visual representations describing how particles move through space and time. Arrows shooting forward, arrows moving backward, electrons turning into positrons, and positrons transforming back into electrons. Yet not a single one of them could make sense of it. Dirac constantly interrupted my presentation with sharp, extremely precise questions that I tried my best to answer, but he persistently pressed on. Teller began to raise objections, and then in a fateful moment, Bohr stood up. Niels Bohr, my hero, the greatest physicist of an entire generation. He declared that I had completely overlooked the uncertainty principle, that my sketching of these lines was unacceptable, that I was not allowed to speak of electrons having a definite trajectory in space, and that this was absolutely not how quantum mechanics worked. He couldn't understand. These diagrams were not literal descriptions, but merely a system of notation, a subtle shorthand. It was a way to organize calculations, but I couldn't explain it clearly. My presentation was rushed and chaotic. I had watched Schrödinger's marathon performance, and after the conference, I was too excited, too scattered, too strange. I was desperate. Then I said I had too much. My machinery came from too far away. No one understood. The idea started with Wheeler's phone call, the idea of particles moving backward in time. No one could see what I saw. But here's the thing about physics. Eventually, the truth prevails. There was a young British mathematician at Cornell named Freeman Dyson. He came from Cambridge in 1947, one of Britain's most brilliant mathematical prodigies. Initially, Dyson thought I was a bit silly. I didn't look like a serious physicist, nor did I act like one. But then Dyson noticed something strange, problems that took him pages of calculations I could solve in just a few lines. He didn't understand how I did it. No one did. But he could see that I was getting the right answers, so he started to pay attention. In the summer of 1948, a few months after my disaster in Pocono, Dyson and I drove cross-country together. 4 days, 2,000 miles. From Cleveland to Albuquerque, I was at the wheel. It was all country roads. There were no highways yet. We got stuck in a dust storm in Oklahoma and got a speeding ticket in New Mexico. Throughout that precious time, we immersed ourselves in deep conversations about the physical universe, the flow of life, and especially about the unique diagrams I had created. Dyson unhesitatingly dedicated all his passion and valuable time to work alongside me. And then, little by little, he began to deeply understand the ideas I was pursuing. When we arrived in Albuquerque, Dyson continued his journey to the University of Michigan, where Professor Schwinger was teaching a 6-week summer course. Dyson listened intently as Schwinger presented his approach, a complex method, just as everyone at Pocono had previously understood. Immediately after that, Dyson caught a Greyhound bus heading straight for Princeton. In the quiet of the night, on a deserted highway in Nebraska, a flash of insight struck him. Schwinger and I, it turned out, were solving the very same problem. No matter how different our methodologies, notations, and presentation styles were in terms of mathematical essence, we were expressing the same absolute truth. Clearly, the theories we developed were completely equivalent. Dyson synthesized all these findings into a groundbreaking paper titled The Radiation Theories of Tominaga, Schrödinger, and Feynman. That work demonstrated to the entire world that my seemingly strange diagrams were not meaningless. On the contrary, they held immense value. They were an entirely new language, surprisingly streamlined, capable of yielding the same results as Schrödinger's complex equations, but in an incredibly short amount of time. In just a few short years, Feynman diagrams became an indispensable tool for every physicist. Their spread throughout the physics community was like wildfire, not because of their superior rigor, but because of their exceptional efficiency and applicability. You could sketch them right on a napkin. Even a graduate student could master them in a single afternoon. And hidden deep within every stroke of each diagram was Wheeler's audacious, even crazy idea. Lines traveling backward in time, positrons, which are essentially electrons moving in the reverse direction of the time flow. In 1965, I had the honor of sharing the prestigious Nobel Prize in Physics with Julian Schwinger and Shinichiro Tomonaga. However, Dyson's name was conspicuously absent from the list of honorees. This was because the Nobel Prize adheres to a strict rule. It cannot be awarded to more than 3 individuals. This is what I mentioned in my Nobel Prize acceptance speech. Join me as I unveil the secret of that fateful phone call where Wheeler's audacious idea was revealed. I confess I didn't fully appreciate Wheeler's idea of the identity of all electrons to that degree. As much as I cherished the discovery that a positron could simply be imagined as an electron traveling backward in time from the future to the past, in a reversed segment of the world line, an idea I cleverly borrowed, and this is the most valuable lesson I gleaned from John Wheeler. Ideas that seem utterly mad often hold extraordinary importance. Not because they are always correct, for Wheeler's one-electron universe was ultimately proven wrong. The mathematical calculations didn't align. The number of electrons and positrons was far from balanced. Yet hidden deep within that error was a kernel of truth, a groundbreaking idea, a way of thinking that forever changed how we perceive matter. And antimatter completely reshaping our understanding. Most scientists often fear being perceived as foolish. They typically choose the safe path, shying away from all risks. They only focus on minor problems where the answers are already guaranteed. Wheeler, however, was an exception. He never hesitated to voice his boldest ideas. He would persistently pursue them to the very end, and sometimes, hidden deep within that apparent madness, lay a priceless treasure trove of knowledge. To uncover novel truths, you cannot merely think safely. You must be willing to embrace mistakes, willing to face the judgment of others, ready to venture into the dark unknown in pursuit of an idea, not knowing if it will yield any results. It was Wheeler himself who imparted that invaluable lesson to me. He called a graduate student and, frankly, shared with him that every electron throughout the universe was actually just a single particle, bouncing back and forth, traversing the entirety of time. Though that idea may not have been accurate, even to this day, I still constantly ponder it. If this story has resonated with your heart and mind, I urge you to reflect. Are you curious about how the greatest minds shaped our world? Hit subscribe now. Join me as we delve into the captivating real-life stories of scientists who shaped our world of